Hello guys, and welcome to the third video tutorial following the second video tutorial of my channel. And just a quick recap from the second video tutorial, we looked at what registers were and how we used binary to represent instructions that are stored on registers. And we started to look at the hexadecimal system, and we said that the hexadecimal system was a system that was based on 16 as opposed to the binary system, and we said it's usually represented by 4-digit codes. We also looked at the different representations of the hexadecimal system by saying 0 is the same as 0 in hexadecimal, 1 is the same as 1, 2 is the same as 2, 3 is the same as 3, 4 is the same as 4, 5 is the same as 5, 6 is the same as 6, 7, 7, 8 is the same as 8, 9 is the same as 9, 10 is actually A. So when it gets from 10 to 15, then it now changes in representation. 10, which is a denary number or decimal number, is represented as an A. 11 is represented as a B in hexadecimal. 12 is represented as a C. 13 is represented as a D. 14 is an E, and 15 as an F. Today we're going to be looking at the conversions to understand how we can convert hexadecimal values into binary and how we can convert binary into hexadecimals. So we're going to be taking the first example here, which is example 1, and we have a binary number, which is a really long binary number. Remember that hexadecimals are represented into a groups of 4 bits, which means 4 ones and zeros. So the first step you need to do whenever you have a binary number and you need to convert it into hexadecimal is to split that binary number into 4-bit representations, and then basically put the powers of 2 on top of each bit to find out what the representation is. So that's what we're going to be doing today, guys. We're going to be working on this, and we're going to start off right now. So let's take a first example that we have. We're going to be looking at activity 1.4, and we're going to be looking at the steps we need to take to convert binary numbers into hexadecimals. So as usual, I'm going to be using this Jamboard to visually represent this so it's easier to understand. So what we're doing today is we're trying to understand how do we convert binary numbers into hexadecimals. So binary into hexadecimals. Okay, so all right, guys, so I just want to put that with the title so it's easier for you guys to follow when you watch it and we don't get confused as to what we're doing for today's video tutorial. So the first example we have on activity 1.4 is, again, example, so I'm just going to write it as 1.4, that way it's going to be easier. So it's going to be just 1.4. And the first one we have is this A example. So the A one says we're trying to convert this binary number, which is represented as 1, 1, and then we have 4 zeros, correct? Yeah, we do. And we have 2 ones at the end. So how do we change this binary number into a hexadecimal number? What we have to do, the first rule is you're going to be looking from left to right, okay? Or right to left, whichever one, but I just prefer to go from left to right. So you look at this binary number from left to right, and then you split it into a group of 4, because we know the hexadecimal system is represented by 4 bits. So that's why we always have to make sure whatever we represent as conversions, they have to be grouped into 4 bits. So we're going to be splitting this into 4 bits. To do that, we're going to be counting from left to right, or right to left in this case. Well, in this case, I'm doing left to right. I just prefer to do it. If you do it right to left, it really doesn't matter. But you need to just make sure you group them into 4 bits. So I'm going to count 1, 2, 3, 4, and I'm going to split it up in the middle here, and we have our remaining 4 bits. So first step is to split the binary number into a group of 4 bits. The second step is to write the powers of 2 on top of those binary numbers that you've just split into 4 bits, and then, of course, multiply them. So I'm going to be looking now from right to left. I'm going to be writing the powers of 2, and we know that the powers of 2 always start with 2 to the power of 0, and we have 2 to the power of 1, and we have 2 to the power of 2, and we have 2 to the power of 3. And then we pretty much go again the same thing. So we don't continue. Remember when we were actually converting binary into denary, we had to continue from 2 to the power of 0 up to the end where we had 8 bits. In this case, we don't continue because hexadecimal is represented in a group of 4 bits. So we don't need to continue. Once we get to the end of those 4 bits, then we stop and then we restart again, putting the powers of 2 from 2 to the power of 0 again, and then 2 to the power of 1, and then 2 to the power of 2. So we keep doing this as long as you have more 4-bit groups that you have divided. So just because we had 3 4-bit groups that we split up, that's why we started as from right to left, 2 to the power of 0 on the top of these first group of 4 bits, 2 to the power of 1, to the power of 2, to the power of 3, and then we moved to the next group, which was again these 4 bits that we had on the left side, and we did 2 to the power of 0, to the power of 1, to the power of 2, and to the power of 3. Now what we're going to do after the second step, so the first step was to split this binary number into 4-bit groups and then represent or indicate the powers of 2 on top of those each bits individually. Now we're going to be multiplying those bits with the powers of 2. So we're going to look from right to left in this case. So 1 in this case times 2 to the power of, I'm just going to write it as its normal value so we don't waste all the spacing over here. So we're going to be multiplying 1 times 2 to the power of 3, which obviously is going to give us 8, because 1 times 8 is 8. So on this side, we have, on the left side, we have 8 plus, and then 1 times 2 to the power of 2, which is 4, so that's going to give us obviously 4. And now I'm going to kind of not multiply this, because even if I multiply, I still get zeros, because 0 times 2 to the power of 1 is 0, plus 0 times 2 to the power of 0 is the same thing as 0. So we still get zeros. When we add them up together, 8 plus 4, we get 12. And then now we're going to be looking at the right side of what we've just done on the left. We're going to repeat it on the right. So this is 2 to the power of 3, and that's going to give us 8. So 0 times 2 to the power of 3, which is 8, is going to give us 0 again on the side, plus 0 times 2 to the power of 2, which is going to be giving us again 0, because 0 times 4 is 0, so 0, and then plus 1 times 2 to the power of 1, which is going to give us 2 in this case, plus 1 times 2 to the power of 0, which is going to give us 1, because 1 times 1 is 1. So what we finally have, guys, on this side is we have 8 plus 4, which is 12, and then here we have 3. So this is our final hexadecimal conversion. However, we must not forget that we said whenever we wanted to represent 10 in hexadecimal, we considered it as an A. Okay, I'm just repeating what we did before. When we want to represent 11, we considered it as a B. And then 12, we actually said it was a C. 13, we said it was a D. Okay, so I'm going to write my C really well here. Yeah, there it is. And then 14, we said it was an E, right? So I'm just recalling what we did before. And 15, we said it was an F. So these were the conversions that we said when we changed them into hexadecimals, how they're represented. So, but here we have 12. We can't leave it as 12 because we have to change the representation of this denary value into a hexadecimal value. So 12 was initially considered as a C, so we're going to write C. And then 3 is the same thing as 3 in hexadecimal. It does not change, so this is going to be a 3. So never leave your final answer. If you get anything more than or equal to 10 in denary and you're trying to convert it into hexadecimal, just make sure you indicate what is the equivalent alphabetical letter for that. And if you get anything from 0 to 9, it's going to be pretty much equal to itself. So our final answer is going to be C3 for this question. So this is your answer, guys. We're going to do another example from the same activity. So we're still in 1.4, and we're going to be doing example B now, and we're going to be looking at what B says. So we've done A and we've gotten the answer to be C3. Now B basically says we have 4 ones and we have a 0 and we have another 3 ones. So we're going to write that down. So we have 1, 2, 3, 4, and then we have a 0. And then we have 1, 2, 3. So I think that's that. So now what we're going to do, again, remember that the steps to convert any binary number into, again, I'm just going to put that there as a clear reminder. If we're converting binary, bin, I represent it as bin, into hex, The first step we're going to do is either look from right to left or left to right. Remember what I said. And we're going to be dividing or splitting this binary number into 4 bits. So we have 1, 2, 3, 4. So we're going to split it in here. And we have 1, 2, 3, 4. So we have 2 groups of equal 4 bits. So what we're going to do next is we're going to be putting the powers of 2 on top of these 4 bits, right? So basically what we're going to have, so I'm going to rewrite them here. So we have our first group, which is 1, 1, 1, and then we have our next group, which is 0, 1, 1, 1. So the next step we're going to be doing is we're going to be putting the powers of 2 on top of each of these 4 bits. So I'm going to be starting in this case from right to left. I'm going to put this as 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. So basically, we now have our total 4 bits covered with the powers of 2. So we always have to start from right to left, from 2 to the power of 0 up to the maximum. And then we do the same thing here. So we do it separately. We don't continue, remember? So we do it again, 2 to the power of 0. We put the powers of 2 on top of each of those bits. 2 to the power of 1, 2 to the power of 2. And finally, we have 2 to the power of 3. So these are our 4 bits, and we've represented or we've indicated the powers of 2 on top of each of those bits. The next step we're going to do is to multiply those bits by the powers of 2. So we're going to be looking on the left side first. So 1 times 2 to the power of 3 is going to be 8, plus 1 times 2 to the power of 2 is going to be 4, plus 1 times 2 to the power of 1 is going to be 2, plus 1 times 2 to the power of 0, which is going to be 1, obviously. And then we do the same thing on the right side. We're going to multiply 0 times 2 to the power of 3, which is 8. So 0 times 8 is going to be 0, plus 1 times 2 to the power of 2, which is 4. So it's going to be 4, plus 1 times 2 to the power of 1 is going to be 2, and plus 1 times 2 to the power of 0, which is going to be 1. So now what we're going to do is add up everything. So 8 plus 4 is 12. Right? 12 plus 2 is 14. 14 plus 1 is 15. So we have 15 on this side. And on this side, we have 4 plus 2 is 6, plus 1 is 7. So we get 15, 7. Remember that we don't leave the representation of a denary value as it is anything from or equal to 10 up to 15 in hexadecimal. We have to write its equivalent value in hexadecimal. So 15 is its equivalent value is actually F. So that means this is going to be F. And of course, 7 is the same thing as hexadecimal as 7. So we don't change anything in this case. So your final answer is going to be F7, guys. So this is the answer for this question here. So in hexadecimal, this binary is represented as F7. We're going to do one more example. I want to take a really long one so we can look at it. So I'm going to just go randomly with some, let's say I do F, or if you'd like, I could do I. So let's do I as an example, and you guys can, practice the remaining exercises from C to H and J because we've done A, B, and now I'm going to do I. So I just want to take a long number example so it's easier or you don't get confused while practicing. So I'm going to write this down. So we have 1, 1, 1, 1. We have 1, 2, 3, 4, 5, 6, 7, 8 ones. So we're going to be writing 8 ones. So again, this is I. I'm doing I. And we're going to be writing 8 ones. So we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 ones and we have a 0. And then we have 1, 2, 3, 4, 5 ones. So we have a 0. And then we have 1, 2, 3, 4, 5. And then we have a 0, 1 at the end. So we're trying to convert this binary number, again, remember, into hexadecimal. So bin binary, I'm going to write it completely this time, into hexadecimal. Okay, so the first step we're going to do, guys, as usual, is we'll look, well, I like to look always from the left to the right. So we're going to be dividing this whole binary number into a group of 4 bits because we're trying to convert it into hexadecimal. So what we're going to do is count 1, 2, 3, 4. I'm going to create the split here, okay, as usual. So split's going to go here for the first group. And then we have 1, 2, 3, 4. Another split's going to go here for the next group. And then we have 1, 2, 3, 4. Another split's going to go here. And we finally have 1, 2, 3, 4. So first step is to split this binary number into a big group of 4. And then we're going to look at our first bit. So we had 1, 1, 1. I think that's too low. I need the space for the conversions. So I'm going to write it here. So we have 1, 1, 1, 1, and we pretty much have the same for the other group bits. So I'm going to write the same thing. We had 1, 1, 1, 1, and then we have the same thing here in difference. 0, 1, 1, 1, and here we have 1, 1, 0, 1. So the next step, guys, as usual, you need to write the powers of 2 on top of each of these bits. So like I said, I prefer to look from right to left. So I'm going to be writing the powers of 2. So here's 2 to the power of 0. Here's 2 to the power of 1. And then we have 2 to the power of 2. And then we have 2 to the power of 3. And then we have to do the same steps for the next 4-bit group. So we're going to write 2 to the power of 0. So from the first bit, 2 to the power of 1, then 2 to the power of 2, and finally we have 2 to the power of 3. So pretty much the same steps, just repeat writing the powers of 2. The same thing goes here. We're going to write 2 to the power of 0, and 2 to the power of 1, 2 to the power of 2, and 2 to the power of 3. So there we have all of them. And then we're going to repeat this again for this on this side. So 2 to the power of 0. So guys, please blind if you don't really see what I'm doing, because I'm choosing a very thick pen. I think I'm going to change the pen thickness to something a bit lighter. So I'm going to use this one. Nope, this one's better. Yep. So 2 to the power of 1. Yeah, I think that's better. 2 to the power of 2. And 2 to the power of 3. Okay, so now that we have our powers of 2 written, oh, sorry about that. I wanted to erase this and write it well. So now that we have our powers of 2 written down properly for each of these 4-bit groups, we're going to now be multiplying the powers of 2 by each of these bits that we have. So we're going to start on this side. So here we have 2 to the power of 3, okay? Times 1, so obviously it's going to give us 8, plus we have 2 to the power of 2, which is 4, times 1 is obviously going to give us 4, plus we have 2 to the power of 1 times 1, so that's 2 times 1, which is going to give us 2, and then plus again, 1 times 2 to the power of 0, which is the same thing as 1, so 1 times 1 is going to give us 1. So we're going to repeat the same thing. Obviously, you already can tell that we're going to get the same results that we got here in here as well. So we're going to have the same thing as an 8 plus a 4. So we have 8 plus 4, and then we have plus 2, and then we have plus 1. So we pretty much get the same values because they're the same number of bits and they're the same bits. And then on this side, we have 0 times 2 to the power of 3, which is 0 times 8, and that gives us 0, plus we have 1 times 2 to the power of 2, which is going to be 4, because 1 times 4 is 4, plus 1 times 2 raised to the power of 1, which is going to be 2, because 1 times 2 is 2, and then plus finally 1 times 2 raised to the power of 0, which is 1 times 1, and it's going to be 1. Then here we have 1 times 2 raised to the power of 3, which is going to be 8, plus 1 times 2 raised to the power of 2, which is going to be 4, so 4 times 1 is 4, plus 0 times 2 raised to the power of 1, which is going to be 0, automatically 0 times 2 is 0, plus 1 times 2 raised to the power of 0, which is going to be 1. So this is pretty much what we get on each group, each 4-bit group. Now we're just going to add them and then convert them into their equivalent hexadecimal value or alphabet. So 8 plus 4 we know is 12, 12 plus 2 is 14, 14 plus 1 is 15. So on the first bit group we get 15 here. And then on the second 4-bit group we get the same thing because they're the same amount of bits and they're the same bits. So when you add this up you get 15, and here when we add 0 plus 4 plus 2 plus 1, so that's 6 plus 1, which is going to give us 7. right? So on this side, we get 7. And on this side, we have 8 plus 4, 12. 12 plus 1, which is going to be 13. So this is our final answer, but remember, like I said, we can't actually leave it like that. When we get any value that is equal to 10 or greater than 10 in a denary number as our result when converting into hexadecimal, we have to find its equivalent as a hexadecimal. So 15 is represented as an F, so F is equal to 15. That's how we represent it. The same thing goes here, F is equal to 15. And then here, 7 is the same as 7. We don't change that, so 7 is 7, right? And then finally here, we say 13 is not represented as 13 in hexadecimal, but rather we represent 13, if you remember from what we've done before, here, 13 is represented as a D. So that's what we're going to represent it now. So which means this is going to be equal to a D. So now we're going to gather our answers. From the first 4-bit group, looking at the left side, we had F. The second one was an F as well. The third one was a 7 because that was its representation. And the last one is a D. So this is how you represent binary into hexadecimal. And this is the answer for this question. So what I'd like you to do is to practice doing C to H yourself as well as J, just to understand and see how you can follow based on what we've done if you understood how to convert binary into hexadecimals. Okay, we're going to move to the next one, and the next one is converting hexadecimal numbers into binary. So the steps to convert hexadecimal numbers is, first of all, we're going to be finding the binary number of each hexadecimal digit, and that will be represented with a 4-bit code, which I'll explain what that means. So once we find the binary number or the binary conversion of each denary, in this case hexadecimal digits, then we'll group them all together into one binary form. So we're moving on to the next example. How do we actually convert hexadecimals into binary? So this is the opposite of what we've just done now. So we have just done how to convert binary into hexadecimal. So now we're looking at the vice versa version. So hexadecimals into binary. So I'm just going to put it as a bin, like bin. So what we're going to do is we're going to be taking the first example. So we'll do 2 examples from here, and then I'll like you guys to practice as usual, or 3 examples. So 6C is what we have, right? So what we want to do is, so this is activity 1.5, okay? So 1.5. Oops, there it is. So what we're going to do first, the first step is whenever you want to convert a hexadecimal into a binary, you have to convert that each individual hexadecimal value into binary first, represented by a 4-bit code. So I'm going to put a partition here as well. So 6, remember that we had the powers of 2, so I'm going to repeat those powers. We started 2 to the power of 0. Because we're going into binary, we kind of have to recall the powers of 2. So 2 to the power of 2, and we have 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, 2 to the power of 7. All right, so its equivalent in denary system is here's going to give you 1, here's going to give you 2, here's going to give you 4, here's going to give you 8, here's going to give you 16, and then here you have a 32, and then here you have a 64, and finally you have a 128. All right, so these are the equivalent values of these conversions. So we want to convert 6 into binary. So we're going to be looking at which powers of 2. Do you remember when we were looking at how to convert denary into binary, and we said we always had to find out what power of 2, when you add them up together, they give you that particular denary number, sorry. So in this case, we're going to repeat the same step. We have 6, and 6 is a denary value, or a hexadecimal value in this case. So we need to look for which power of 2, when we add it up, gives us 6. Obviously, it's not going to be anything from here. So if you're looking from left to right, it's obviously not going to be anything of 128. That's not going to happen. I don't even need to put a 0 because we're representing hexadecimals as a 4-bit group. So what you can do is just, cancel out. You just need 4 bits, that's all, to represent one particular hexadecimal value. So this is obviously a no-no. This one too is a no-no. 64, no, it's too big. 32 is a no-no. 16 is a no-no because they're all bigger than 6. We're converting 6 into binary. 8 is a no-no. However, 4 is not a no-no. It actually is true because 4 is less than 6. So we can say, we can say 1 here. And then we can also say, so if we say 4, yes, as in 1, we're representing as yes. Remember I said you'd have to subtract that number that you just used. So 6 minus 4, which is going to be 2, we're left with 2. We still have to continue to add up to see what we can add, what power of 2 can add up to give us 2. And then when we get a remainder of 0, we stop. So we're still left with 2. We continue to look from the left side, from the right side. So 2 is yes as well. So that means that 2 minus 2 is 0. So that's good. We need to stop now because we no longer have any remainder. And then for 1, because we want to convert this denary number into this hexadecimal, digit into binary, we're going to be representing it as a 4-digit code. So we can't just write 11 because that's not a 4-digit code. That's a 2-digit bit code. We need to use the law of representing hexadecimals as a 4-bit group digit code. So what we're going to do is, okay, so we said 4 plus 2, that's definitely what's going to add up to give us 6. For the remaining one, we're going to put a 0 in front, okay, because 1's a no. And we're still going to add a 0 at the back here. So because we still have 3 bits group code, we need a 4-bit. So we're going to add zeros in the places where we don't need them. So instead of saying a no for 8, we're going to add a 0, of course, here. So we'll put a 0 here. Why are we doing this? Because we need to make sure that we have a 4-bit group to represent each hexadecimal value when converting into binary. So we can't just write a 1 because we're not doing it into a denary. So we have to actually add those extra zeros where necessary to make up a 4-bit. So here we had to add the extra 0 on top of the 8, and we had to add it on top of the 1 to complete this 4-bit code. So which means for 6, we finally get 0, and we get 1, 1, 0. So we finished the conversion of this hexadecimal value into binary. So we're going to look at the next one. So I'm going to erase all these x's that I put on top of the powers of 2, and we're going to convert C hexadecimal value into binary. So now that we want to convert C hexadecimal value into binary, again, if you recall before, we said A was equal to 10, right? And we said, so this is in the hexadecimal representation. B was equal to 11, and we said C was equal to 12. So which means we're supposed to convert 12 into binary because that's what we have. We don't have a C, we have 12. So the representation or the equivalent value of this hexadecimal in denary is 12. So we're going to do the same steps again. We're going to be looking at the powers of 2 to see which one actually adds up to give us 12. So of course, if we start from left to right again on this side, 128 is a no-no, 64 is a no-no, 32 is a no-no, 16 is a no-no because all these numbers are greater than what we need to convert. 8 is actually not a no-no because it's smaller, so we put a 1 on top. Yeah, 8 can go. So we're going to do the quick math again here, so which means if we used 8, we're going to subtract it from 12. So that would be 12 minus 8, and we're going to get a value of 4. We have a remainder of 4. We still have to keep going. So we go to the next one, and perfect. We have 4. So we say, yes, it's actually is equal to 4. So we subtract 4 from 4 until we no longer get a remainder, and we get a remainder of 0. So that's good. So we still cannot write the answer as 1, 1. Remember, because it is hexadecimal, we must represent it as a 4-bit group code. So which means we're going to be adding those extra zeros where necessary. So in this case, we're going to add it in front here. So we had 1, 1. So we're going to add a 0 to 2 because we no longer need it. And we're adding a 0 to 1 as well because we don't need it for this add up. We only had 2 digits of powers of 2 that add up to 12. So we have 1, 1, 0, 0. So the equivalent conversion of this denary number into binary, denary number into binary is going to be a 1, 1, 0, 0. Again, I reiterate, the reason I'm adding these extra zeros is because as the rule for hexadecimals, they must be represented using a 4-bit a group of 4-bit code. So this is why I'm including these extra zeros where necessary, whether it's at the back if we needed to, or it's in the front that can make up to these 4 bits. So what we do now that we have our complete answers. We finished converting each individual hexadecimal value into binary, which is what we did. The last step to be able to get our answer from hexadecimal into binary is to join up all these binary group digits that we just got into one. So we'll join these two together, okay? So what does that mean? We finally have an answer of, if we look from left to right again, because we're joining them, we're gonna get 0, 1, 1, 0, and then we have 1, 1, 0, 0. So this is our final answer, guys. This is our answer for this question 6C of how we convert binary into hexadecimal, into binary from this to this. Okay, I'm gonna do one more example for you guys, and I'd like you guys to practice the rest on your own as practice work to see if you understood. So the next one is B. We're gonna take example B. And the hexadecimal we have is 59. Don't read it as a 59, guys. These are two separate values in hexadecimal, so we read it as 59. So the same thing goes again. We're going to be looking for, so the first step is to look, split these two numbers or three numbers or whatever numbers you have into parts. So I split them up into parts. The next thing we're going to be looking at is what power of 2 can add up to give us this first hexadecimal number. So the first one is 5. So what power of 2 can we add up to give us 5? Again, if you recall from the previous slide, 2 to the power of, so we're going to look for what power of 2 gives us 5. So 128 obviously is a no-no. 64 is a no-no because it's bigger than 5. 32 is a no-no. 16 is a no-no. 8 is a no-no. However, 4 is not a no-no because 4 is actually smaller than 5. So we can use 4. So we're going to say yes for 4, which means we put 1 on top. And now if we subtract 5 from 4, we're going to get a remainder of 1. So we have to keep going again. So I'm just repeating the steps we did. So we still have a remainder of 1. 2 is going to be a no-no, so we're going to put a 0 on top because we need to represent it by a 4-bit group. So 2 is 0, which means no, because 2 is bigger than 1. We have just 1 as a remainder. And 1 is actually perfect because it's equal to 1, so we're going to say yes. When we subtract that 1 by 1, because remember we initially had 5 minus 4, we got a remainder of equal to 1. Now we're subtracting 1 minus 1, and we're going to get no remainder. So that's where we need to stop. So 1 is yes, but we still have just 3 bits of 3-bit groups, and we remember for hexadecimals we need to represent by a 4-bit group. So what we're going to do is we're going to just add this extra 0 here in this case because that's the closest one to the 3-bit group. So we're just going to add a 0 here on the left. So we make it as a 0, 1, 0, 1. So in this case, 5 is represented in binary as a 0, 1, 0, 1. So just typically like what we did before of how to convert denary into binary. Now we're going to look at what is the representation of 9 in binary. So it's the same thing again. 128 is a no-no, 64 is a no-no because they're all bigger than 9. 32 is a no-no, 16 is a no-no. However, 8 is not a no-no because it's actually smaller than 9. So we're going to erase all this and then we'll put the values that we have. So 8 is smaller than 9, so we're going to put a yes on top because we can use it to subtract from 9. So 1, yes. So since 8 is smaller than 9, we have to subtract 9 from 8 as we normally do. So we're going to get 9 minus 8. And we have a remainder still, so we need to keep going, a remainder of 1. So we still have 1. 4 is greater than 1, so it's going to be a 0. 2 is greater than 1, it's going to be a 0. However, 1 is not greater than 1, but it's equal to 1, so it's going to be 1. So this is perfect because we have exactly our 4-bit group code, so we can just represent a 9 as 1001. So we don't need to add any extra zeros in this case. So 9 is actually 1001. So now we're going to do the last step. Once we've converted each of these digits, hexadecimal values, into the respective binary, we're just going to join the whole binary groups into one. So our final answer is going to be 0, 1, 0, 1. And of course, we're going to have 1, 0, 0, 1. So this is our final answer, converting this hexadecimal value into binary, guys. So this is where I'm going to be ending this video tutorial for today, because I would like you to try to practice what we've done. Use some of these exercises from C to H up to J to practice and see how you can change binary into hexadecimal. And the same thing goes for activity 1.5. From C to J, try to practice of how you can change these hexadecimals into binary, and also H to J. The next time we come, we're going to be learning how to change hexadecimals to denary and denary to hexadecimals, and we're pretty much rounding up this topic, and I'll be starting a new video tutorial on Java programming as well as Python. So I hope to see you guys in the next video, and I wish you guys a great day and enjoy. See you, everyone.